adventures in the theoretical sciences. It's a pleasure to have all of you here. As you know, this is a series of lectures. Each week we have one lecturer giving two-hour lectures, Thursday and Friday. We're all experimenting with format, so I will let each speaker tell you about how they're planning on using the time. I'll remind you that with so many people in the room, it's useful to be muted unless you're called on. And other than that, I think we can get started with the substance. It's a great pleasure to have David Schwab speak to us today. David is a faculty member at the Graduate Center of the City University of New York, where he's one of the core members of the Initiative for Theoretical Sciences. He came to us from Northwestern University, where he was on the faculty in physics and astronomy for several years. He did his PhD at UCLA and spent his time as a postdoc in Princeton. He's worked on a wide variety of problems in the physics of biological systems, more recently in things related to machine learning. And today he is going to talk about the interface between statistical physics and machine learning. So, David.
Great. Thank you so much, Bill. I'm really excited to be here today. This is a new experience for me in the sense that, you know, although I've taught a number of courses, this is an order of magnitude at least more than the number of students I usually reach. So it's an experiment for me. So bear with me as we go along. So as Bill said, I'll be telling you about statistical physics and machine learning today. Actually, just to check, you can see my cursor, is that correct? Someone that is not muted or somebody in the chat.
No, I don't see the cursor.
Oh, you don't see my cursor. Interesting. Okay, that's good to know for, you won't see what I'm pointing at. Okay. Okay, so.
There should be a way to make it work, but it might.
It was working yesterday.
Referring to the lower left might be easier than trying to figure out how it works.
Right. Right. Okay, so let's see. So these two lectures will not be a general introduction to machine learning in the sense that I won't be giving you a list of topics and approaches going through linear regression and logistic regression and Gaussian mixture models and whatnot. Instead, my goal here is to give you, I hope, a handling on some essential concepts that I think are useful in general for knowing about machine learning, and give you some grounding so that you can go off and read you know, details of those and other methods elsewhere, but also with a view towards statistical physics, which is the main objective of these lectures. And so in particular, I'll be focusing mainly on what's called supervised learning, and I won't cover other topics such as unsupervised or self-supervised or generative models. This includes things like GANs or variational autoencoders. If you've heard of those things and you want to hear about them, they're fascinating, but they won't be in these lectures. We won't cover anything in reinforcement learning. This is the subject of an agent exploring an environment and trying to figure out how to behave to maximize its reward. We won't be covering that, and we also won't be covering sequence models like recurrent neural networks or hidden Markov models or recent developments in natural language processing. So if you're interested in those things, I'm happy to give you references. Feel free to email me, but they won't be in these lectures. So let's see. Okay, so for the format and the logistics of the way these lectures will go, I think our experience thus far has been that the chat is a pretty effective way to ask questions. So I encourage you to ask questions throughout, at any point during, on any slide, directly in the chat. And I have the chat up, and we'll try to monitor it and answer questions in real time. Um, that said, there will also be sort of dedicated time for questions. I'll take a 10-minute break about halfway through where you can get up, get some coffee, whatever. But I'll still be here to answer questions about the material or anything else. And then there'll also be dedicated time at the end for broader questions. I had a few people email me asking me about some things sort of more research level. The broader questions at the end of the lectures would be a good time to ask those. Great. So I hear that my cursor is now visible. That's great. And then as Bill mentioned before, just for everyone's for everyone's benefit, if you keep your microphone muted, unless you're asked to speak, that'd be great. There are sometimes questions that are difficult to type, and it's easier to just speak them. So that's totally fine, no problem. Just either raise your hand, in which case maybe one of the other co-hosts can let me know that you've done that, because I don't have that up right now. But you could also just in the chat say that you'd like to ask a question. Okay, great. So you might be wondering why this mashup of two very different things? Why statistical physics of machine learning? And there's sort of two reasons that I think this is a reasonable combination. One is not specific to machine learning, but it's simply the statement that to me, physics is the art of building simple models that have predictive power. And I don't care if we're talking about actual particles, or if we're talking about neuroscience, or if we're talking about sociology. If what you're doing is building simple models that nonetheless try to make real predictions, then I think it's reasonable to consider that physics. And the goal of these simple models, I've lost my cursor again. The goal of these of building simple models is often towards revealing general principles at work, and that might give you a hint to why these simple models work. So if you're doing that, I think it's reasonable to call it that physics. Again, that's not specific to machine learning, but the second reason is slightly more specific, which is that many of the modern methods, like deep neural networks, are interacting systems with many degrees of freedom, in which case you might think that they're amenable to an analysis based on statistical physics. And so we'll see examples of that later on. And now my cursor is turned. Great. So here's a really brief outline of the lectures. So today I will first give you a very high-level overview of what I think are essential concepts in machine learning. In particular, focusing on things like the Biasvariance decomposition. It was so central that we put it in the title of a review paper that my colleagues and I wrote last year, that I will be basing the bulk of the first lecture on. So if you want more reading material on this lecture, I recommend checking out this review. Another nice feature of it is that it includes a collection of around 20 Jupyter notebooks to implement most of the figures and many of the concepts that we talk about, so that you can actively play with these methods. So you can check those out here at this link. So after discussing some of these core concepts in machine learning, I'll give you a very brief introduction to neural networks. And I will close with a couple of modern mysteries. So what is it that has made people excited about neural networks in recent years, not just from the practical standpoint, but from the theoretical standpoint. In what ways do they seem to violate sort of classical theory that we have, and lead to the idea that there's something else to be discovered? So that's today, and then tomorrow I will dig deeper into the sort of physics of machine learning. I'll first start by going through a statistical physics formulation of a learning problem that comes from Elizabeth Gardner in the 80s, that I think is pretty instructive as a way both of learning about learning, but also learning about statistical physics. So I'm sort of assuming that many of you in your undergraduate experience might not have had the most exposure to statistical physics, and I personally find that learning about statistical physics through the lens of a learning problem actually helps me understand statistical physics better, and that will be part of the objective of this part. And then in the last part, I'll tell you about a recent paper that a grad student and myself worked on how noise during training can provide useful entropic forces that guide learning into certain directions. Okay, so maybe I can pause for a second if there are any questions that come up. Otherwise, I'm going to get into the material. Okay, so lose my cursor every time I change slides. Okay, so sorry, I'm having some difficulties. Okay, so let's first think about what is learning. So what I want to do here is a sort of experiments, and I'm not going to go into details of how you do this experiment, but I think we can get the ideas nonetheless. So what I'm going to do in the top row of figures here is I'm going to sample 10 points on the left from a line. That's all I've done. And then I'm going to take those 10 points and I'm going to fit to them either a line, a third order polynomial, or a 10th order polynomial. And in all cases, because a 10th order polynomial can fit these 10 points by just setting all of the coefficients except the linear term and the constant to 0, all of these models fit the points perfectly. And then what I can do is I can generate more points from that line, and I can even go beyond the range. So on the left, I sampled points from the range 0 to 1, and now on the right I've sampled new points beyond the range 1, and I can look at how well these different models predict these points, and they all perform perfectly. Okay, great. Then what I can do is on the bottom row, instead of sampling points from a line, I could sample points from the 10th order polynomial, and I could do the best job I can fitting those 10 points either with a line, with a cubic, or with the 10th order. And you see on the left that the 10th order fits the points correctly. The cubic does a moderately okay approximation, and the line does the worst job, as you would expect. And when you try to predict new points, again, the 10th order does perfectly, the cubic does less good, and the line does even less good. So the main thing I want to emphasize here is that this is very much not a learning problem. And what looks more like a learning problem is if instead you add noise to your objective. So what I've done here instead, and I want to try and get my cursor back if I can. failure. Huh. Give me 1 second. I will try. Hang on 1 second. I'm going to try closing this. No luck. Okay. Okay. So what I've done here is I've performed the same kind of experiment, but instead of just on the top row sampling points from a line, I've sampled them from a line, but then added noise. And what you see is then tried to fit those points, now 100 of them instead of 20 or so, with the line, with the cubic, with the 10th order. And as you make the function that you're trying to fit more complex, it fits more of the wiggles of the training data, but it starts to perform worse when you make predictions on test points. In this case, in particular, when you try and make predictions beyond the range x 0 to 1 that you sampled points from. So the 10th order polynomial is doing something very weird beyond the range 0 to 1. And on the bottom, again, it's the same experiment, but where the true data generating function was a 10th order polynomial with noise added. And even here, where the true model was a 10th order model, if I look at test points beyond the range of 0 to 1, here the cubic actually performs better. So a model that we know is not the right model is actually making better predictions. Sorry, I'm really having trouble with not being able to see my cursor. Okay, so you can continue this, and you can say, well, what if I, here I had 100 points and there was noise. What if I added more points? And so now we've added 10,000 points. So we have 10,000 points drawn from this 10th order polynomial, and we fit it over the range 0 to 1. And you might think that that you can do a pretty good job of finding the right 10th order polynomial. And on the right, you see that you do in fact do a pretty good job over the range 0 to 1. But then when you ask it to make predictions outside of where you fit it, it starts to fail miserably, whereas the cubic actually does better. So the lesson from this is that even if you know that the true model is of a certain form, oftentimes fitting a simpler model can make better predictions. And I should say that these plots all come directly out of, I think, the first Python Jupyter notebook that we have. So they're more illustrative if you open it up and run things and play with things than any particular example. And then you can actually plot the performance of the models and so on. Okay, so what I want to do next is I want to go through some sort of fundamental classic intuitions from the theory of learning. And this will ultimately get us to the Biasvariance decomposition. And I want to emphasize at the outset, one of the reasons why I am focusing on this is that although it's a very sort of fundamental result in classical perspective on learning, it seems to be violated in a sense in modern machine learning. So we'll get to that at the end of the lecture, the way that these very foundational kinds of ideas are actually not not correct for modern models. So the idea here is, first we want to make a distinction between our error when we make predictions on the data that we fit our model on, and the error when we make predictions on new data that we didn't fit our model on, but nonetheless comes from the same data generating process. And so here I'm going to call those E in for the error, what's called in sample or on the training data, and E out for the error that's on the testing data or the out of sample error. And on the left, I've plotted the number, these errors as a function of the number of data points. And what you see is that generally your ability to make predictions on new test data gets better as you get more data points. So E out is decreasing as you get more data. The in-sample error on the training data actually goes up as you get more data points. This might be a little bit counterintuitive, but think of this like if I am fitting a 10th order polynomial, but I give you 4 points, then I'll be able to fit it. And as I give you more and more points, I won't be able to do as well on each point individually. As you increase the amount of data, eventually these two errors on your training data and on your testing data will asymptotically approach each other. And the value that at which they approach each other is something called the bias. And I'll be a little bit more precise about this later. But there's this fundamental floor that they both tend towards. And then the added error on the out of sample or on the testing points beyond this asymptotic error is called variance. The reason it's called that is this extra error arises because when you don't have that many data points, any particular realization of your data set, if you lived in parallel universes and you got different samples in each one, you'd get slightly different values of the error. And on average, that will give you some extra contribution. And so this extra component due to the variability in your data set is called variance. And then there's a third concept, which is the difference between how well you perform on your training data and how well you perform on the test data, and that's called the generalization gap. So the goal of learning is not to have a small error on your training data. If you use a big enough model family or a big enough function family, you can always do that. The goal is to have as small as possible test error, and the gap between training and test you would therefore like to make as small as possible. You would also like to have some confidence that when you fit a model to some data, when you go out and use it in the real world, it will perform similarly to how it did when you trained it, and the generalization gap is related to that. So this is your error as a function of the number of data points. If I was fitting a particular kind of model, what you can do instead is you can hold fixed the number of data points, and now we'll vary the complexity of the model. And I don't want to get into details of how I quantify complexity of the model. Let's just keep it schematic. But what you generally find in sort of classical, except in the recent years, is that as you increase the complexity of the model family that you're fitting, this term that I've called the bias goes down. And the idea is that this bias is a sort of fundamental limit on how closely I can fit some complex data with my limited function. If I only can fit lines, I'm sort of biased in the kinds of predictions I can make. And as I go from fitting lines to cubics and so on, I'm more flexible, and therefore my bias should go down. At the same time, I have more parameters I need to fit. So when I have a finite data set, this component that I was calling variance actually increases as you increase the model complexity. And so there are these two terms trading off, and what you expect to find in many cases is a minimum of this out of sample or test error at some intermediate level of complexity. And so what you would like to do, since what you get paid for is making out of sample predictions, is to find that intermediate level of complexity that gives you the smallest out of sample error. One other view that you could take on this is drawn schematically here, where I imagine that here I'm in sort of model space, and let's say that the true data generating process is the red dot, and then I look at what happens when I collect samples from that data generating process and then fit two different kinds of models. In one case, I have a very flexible model that in fact includes the true model. So this is like fitting a 10th order polynomial to data that was generated by a 10th order polynomial with noise. And what you find is that for every realization of the data set, you get slightly different models so you get a sort of cloud of possible models, and the true model might be inside of that, but there's a large variance around the possible models that you learn. On the other hand, if you had a smaller model family, you might not be able to get to the correct model. So in gray, the smaller model family doesn't include the true model, but it has a much smaller variance in that every time you draw another data set, you reliably get a similar kind of model. So it's very possible that you might prefer the low variance model with some bias, because you're on average more likely to be close to the true model. So what these are very schematic, and what I want to do is try and make this a little bit more precise with a simple little calculation that I hope helps you build some intuition. So what we're going to do is try and derive the sort of decomposition of the error on test points in terms of things that look like a bias and a variance and another component. And so what I want to imagine is I have some data set of points. I have inputs X, and I have predictions Y that I want to make, like I was doing in those plots on the first couple of slides. And I'm going to imagine that it's generated from some noisy process where there's some true function f of x, and from that I add some noise, and then I'll get my sample y targets from that. What I would like to do is to fit a model or find a predictor, which in our review, and I've stuck with this notation, but it's unfortunate, we also called f. So just to be very clear, there is no relationship in principle between the f that was the data generating process and the model f here. So the way you can distinguish it is if the f has the second argument that is a theta, which is a set of parameters, then that's a model that you're fitting to the data generating process. That may or may not include the f of x that is the data generating one, for a certain value of the parameters theta. So what we're going to do is we're going to try and fit this this model f of x and theta to the set of samples that we have from the data set by minimizing the squared error that we make. And here I'm calling this this a cost function. I was sort of schematically referring to this cost as an error on the previous slides. And this is something that is maybe worth getting used to in this field. Like a lot of these concepts were, came from many different fields in parallel, and sometimes they mean slightly different things, but in many cases, you'll see people use the term error, loss, and cost all sort of synonymously. And I'll mention later on some subtle differences, but here you should think of this cost as similar to the error that I was referring to previously. And what we're going to try and do is fit the parameters so that we minimize this cost, minimize the squared deviation that of the predictions our model makes on the points that we have. And one thing I want to emphasize is that once you do this, the value of the parameters that you learn, the theta hats, where I put a subscript d, are now dependent on the samples of the data set, the samples of the data that you have in the data set. So that's why I have this subscript d. Okay, so what I want to do now is I want to look at this this cost, and I'm gonna try and compute what this cost is after I have fit my model on new samples. So now I'm gonna look at my test costs. So I'm gonna put a new data set of samples, or a test data set, and I want to compute the average cost. And when I say average costs, I mean two things. I mean an average over realizations of the data that you might have had. And I also mean an average over the noise that might be in the testing samples. So you can take this squared difference, and we can do a trick which happens all the time, adding and subtracting the same things. We're going to add and subtract the true function evaluated at each data point, and then break it off into three terms. Right? There's the first term squared, the first two terms squared, the second two terms squared, and there's the cross term. And the first thing you can notice is that the first term, we're going to assume here that we had added noise epsilon that was zero mean with some variance. So this term will just be related to that variance of the noise. There's no model here. This is really just yi and f, which is the true model, exabi. So this is just something about the inherent noise in the data generating process. Then the third term will actually disappear, because the first component, which is a difference between yi and the true function f evaluated at xi, will on average over realizations of the noise be zero, again because we assume that the noise has zero mean. So all we have really is this second term, this middle term, and coming along for the ride is this extra noise floor that we can't really get past. So now let's look at the second term, and let's massage it a bit more. What we can do the same trick again, where we add and subtract the same thing, but now what we add and subtract is a property of the model. So now we're going to take the model evaluated at the point xi, using parameters that are learned from the data set, but then also averaged over realizations of the data set. So this is sort of like the prediction of the average model that you learn, or it's the average prediction of the models that you learn. And then we do the same thing, look at the first two terms squared, second two terms squared, and then the cross term. And now you'll notice that if we look at the cross term, we have an average over data sets, but in the first, I really wish I had my cursor, in the first bracketed term, there is no data set dependence, so we can pull the average over data sets through, and now we just have the average on the last bracket of the difference of these two terms. And you can see now that that's actually going to be 0 because the second term is the average over data sets of the model, and the first term will inherit the average over the data set. So that the cross terms die away, and we have just these two squared differences. And these are the two terms that we can give an interpretation as being related to a bias and a variance. Here I've actually written it as a bias squared, and it sort of refers to the squared difference between the true function evaluated on the test data points and the average prediction that your model makes averaged over the data sets. And the variance, on the other hand, tells you over realizations of the data sets, how much do your predictions, do your model predictions vary? So again, the bias term is something related to the difference between the true model outputs and sorry, the true data generating process outputs and your average model outputs. Whereas the variance is related to fluctuations of your model predictions over realizations of the data set. And then there's this third component that is this noise that you just fundamentally can't predict. Okay, so does that make some sense? I hope it was somewhat clear without being able to point to terms. So this is a good moment to, if you have any questions on this decomposition, to type them in. Otherwise, I will change topics a little bit. So I think these notions of bias and variance are pretty fundamental to sort of classical notions of learning, and they're really good to keep in mind. And we're going to keep an eye out later for when they actually seem to not hold for modern neural networks. So a lot of as I was saying, a lot of the excitement in machine learning in the past decade has been in using neural networks as the model family. I should emphasize here that this derivation doesn't depend on the model family at all. There's no linearity assumption of the model or anything. This is really, if you have squared error, this is a decomposition of the squared error. So you could imagine that your predictor here was a neural network and your data generating process F was something very complicated. But in recent years, the predictors that have been very successful have been neural networks, and you might ask why is it, and I'll come back to why now for neural networks. But what are some features that make neural networks nice models to use? On the one hand, the idea is that they learn multiple different levels of features or representations, and emphasis here on the learning part. So rather than having to sort of handcraft some features that you think are important in the data for making predictions, they can sort of learn those features on their own.
David?
Yeah.
There's a question. There's one technical question which maybe you want to deal with before you move on.
I'm not seeing anything. Is there chat?
In chat, yeah, it was about the last cross term.
Oh, I didn't. The chat wasn't scrolling. Sorry. Actually, can you see my cursor here?
Yes.
Now you can. Maybe I actually won't go full screen and try to make it so I can point to things better here. Let me go through.
David, sorry, I don't know if you see an annotate option at the bottom of your screen, but if you can see it, you might be able to use a zoom pointer using the annotate option.
I don't see that.
Okay.
I must have an old version of Zoom on this computer. Okay, so let me go back now that I can point to this. I think this was the question. So the question was on this cross term, or sorry, here on for this cross term. Why does this go to 0? The reason is that this average over the data sets, we can pull through to here because there's no data dependence here anymore. This term is already averaged over data sets, and this is just something about the test data. So we bring the average over the training data sets through to here, and now this average, this is already averaged over those data sets. So we just pull it through to this term, and now we get the average over data sets of F, the model, minus average over the data sets, F, the model. So it cancels, and this term is 0. I'm hearing that I can do something for slideshow. Oh, thank you. I think this will, see if this fixes it. Now, can you see my cursor?
Yes.
Perfect. Yeah. Thank you for the tip. Great. I was talking about neural networks and why they're useful models. So we talked about learning features instead of hand designing them. There's also been over the years a lot of discussion about the inductive bias of having depth, and I'll get into what that means more later. I think there's a lot of research left to do there for fully understanding the inductive biases in neural networks, but you might say that empirically the fact that they work so well on certain kinds of data might indicate that there are useful inductive biases yet to be elucidated. A third, sort of sociological reason why they have been popular in recent years is that there are frameworks for coding them that make them very easy to use and easy to customize. And we'll come back to this a bit more later. So let me give you a one-slide introduction to what neural networks are. I'm sort of assuming that you have seen this before, and this is mainly just a refresher. But the idea is we're going to have a bunch of units or neurons, and what they're going to do is they're going to receive input. So the first input layer might be a collection of pixels or a collection of neural activities or whatever, and they're going to receive their input and apply a sort of affine transformation. So they will multiply each each input they get by some weight, and then potentially add a bias to it. So they're doing some sort of linear transformation on their inputs, and then they're going to take what they get out of that and run it through a nonlinearity. Could be a tanh, or it could be more common in the past decade or so is something called a rectified linear unit, where if the result of this linear transformation is below some threshold, they're just turned off. But if it's above that threshold, they just increase what they output linearly. And then from there, they send their output further down the network. So the first layer of these units receives input directly from the data, but then after that, the subsequent layers, instead of receiving data directly, receive the outputs from the of these nonlinearities from the units in the previous layers. And ultimately, let's say you want to make predictions on not continuous predictions like we were talking about before, but discrete predictions. If I think this is an image of a dog versus a car, so you decide you have a certain number of classes, capital M, then after transforming your outputs to make predictions that sort of sum to one, you have some error term, or some error function or cost function that is often something called the cross entropy. This is maybe a good moment to emphasize a difference between a cost function and what you actually care about. So what you might actually care about is how well you predict whether it's a dog or an automobile in an image. But that sort of hard decision is not differentiable. So you need to come up with a cost function from which you can take derivatives, because we're going to need that to optimize the model. So there's an art in finding good cost functions that aren't exactly what you care about, but they contain the essence of what you care about, so that when you minimize them, you will also minimize your error and maximize your performance in the thing that you actually care about. Okay, is this working again? Yeah. So as I was saying, we need to optimize this function that the neural network computes, and this is usually done with what's called stochastic gradient descent. Again, I'm assuming that you've probably seen these kinds of things before, but the idea is if you can usually decompose your cost function as a sum of costs or errors on individual examples. So there was a question. Let me go back if I can figure out how. So sorry. The y's in this cost function are the data that are the predictions you're supposed to make. So this will be for any sample, the ith sample, it'll be a one hot vector where one of the little m's will be set to 1 and the rest will be 0. And that'll be telling you the label on that particular sample. And the y hats are the output predictions of the model, and you're trying to make them as similar as possible. Let's see. So let's see. So a couple of questions. So what we're going to do is is we're going to choose the cost function at the outset, and we don't fit the cost function to the model. We fit the model to the cost function, and usually we choose the cost function before having done anything. So cross entropy is one of the standard ones that is used for a wide array of models that are making categorical predictions, is what you would call this. The y's are not probabilities. The y's are labels. So your data set would consist of inputs x, like we had before, and y's. And the y's in this case, instead of being a continuous number like in the previous examples, they're now a discrete labeling where every input gives you a one-hot representation of whether, you know, the dog might be get a y of 1, 0, 0, etc., and then the automobile get a 0, 1, 0, 0, 0. And the y hats are closer to having a probabilistic interpretation, but the y's are simply labels. And y hat are different. There's a question. So y is the data, and y hat are the predictions from the model, trying to reproduce that same sort of one-hot representation as close as it can. So as I was saying, the error you can usually decompose as a sum over the individual errors on your samples in your data set, and you can then take the gradient of the entire error by just pushing it through and looking at the gradient on every sample. And then the way that you update your parameters is by moving in a direction that is opposite the gradient with some scaling eta, which is called the learning rate. So you move your parameters against the gradient with some step size. And this is called gradient descent. In practice, if you have a data set that is huge, so that your number of samples is millions or more, that's not feasible. It's not feasible even if it's less than millions. What you can do is, instead of computing the gradient on the entire data set, you just take a small batch of your data randomly selected, and you compute the gradient on that random selection, and call that the gradient on the mini batch. And oftentimes this will be a roughly order 100 size, and then you do the same thing as before, where you just step in the direction opposite this gradient with some scaling factor. And this is called stochastic gradient descent instead of gradient descent, because the choice of the samples in the mini batch is going to add some noise to your estimation of the gradient, and thereby some noise to your motion. And one of the things I'll talk about next lecture is some work that we've done on exactly what that noise is doing from a physics perspective and how it might be useful. I should mention that this idea of using mini batches on your of your data instead of the entire data set was originally for computational reasons, to say, hey, it's expensive to compute this full gradient. Maybe I can get most of the juice of that computation by just using a small batch and getting a pretty good estimate. And I'm pretty far from where I want to be in parameter space anyway, so maybe it's not worth getting a really good estimate of those of that gradient. Maybe I'll just use this batch, and that's totally reasonable. But it's even better than that. It turns out that in many cases, by using these batches, you actually get performance that is better than if you use the full gradient. And what I mean by performance, I mean that you get a model that might fit the training data that you have equally well, or potentially slightly less good. but it will generalize the new data often somewhat better. So the question, do you need to iterate over all possible batches? No one told you that you have to, but if you don't, then that means that you have data that you didn't make use of. And usually if you have data, it would be good to use it, because you can estimate your model better. Finally, you can add what you might call momentum, where you say that this v term here, let me inherit from the previous time that I computed this mini batch mini batch gradient, with some scale factor, and then I'll compute a new batch as well. And this will help you find sort of coherent directions with a very weak gradient, for example. So optimizing via stochastic gradient descent with momentum is sort of canonical for neural networks. Isn't the choice of batches adding a combinatorial complexity to the algorithm? So usually you don't choose the batches in a carefully designed way, in some sense. The things that you want, the sort of design questions that you have to think about are, do you sample your data set to get these batches with replacement or without replacement? And do you want to balance your classes in the mini batch and so on? But like you're not carefully optimizing like exactly what goes into the batches typically. There's sort of 4 different regimes of optimization behavior when you optimize via gradient descent that are worth sort of keeping in mind. And here's just a one-dimensional Gaussian as an example. You start with your parameters over here on the left, and you're going to optimize with gradient descent. If you use a step size or a learning rate that is very small, then you just take little steps and you slowly move in to find the bottom of the error. If you really had a Gaussian and you were some distance away, you would get there in one step with sort of Newton's method. There's an optimal step size that you could take. If you are bigger than that optimum, then you'll overshoot the minimum. So you'll shoot to the other side of the error, and you'll sort of ping back and forth until you fall in. But you'll still eventually fall into the minimum. But if you're twice what this optimal rate is, then when you ping to the other side, if you were again perfectly quadratic, then you would be slightly higher, and then you would bounce outwards, and you would end up exploding and flying out to somewhere else. So the learning rate is important for the behavior of the optimization, and this is again only a one-dimensional example, and you have to contend with these sort of 4 kinds of behaviors in all different dimensions. So you have to worry about curvature in all different dimensions, and you have to be worried about this kind of behavior for the worst direction, let's say. Hopefully this builds a little bit of intuition. So this is a generic sort of sketch of how you would optimize any model with gradient descent. For neural networks in particular, you do this via something called backpropagation. And it used to be the case that if you wanted to code up a neural network, you had to go through this by hand, where essentially you say, how does my error depend on the outputs of my last layer, and how do those depend on the parameters that fed into them, and so on, and sort of backpropagate that all the way through. And doing that is called a backward pass of the error derivatives. And there's a in one sense it's quote unquote just the chain rule, but in another sense there's a very nice elegant interpretation of this. It's been invented many times, popularized by Jeff Hinton in the 80s, but invented many times otherwise. The nice thing in recent years with things like PyTorch and TensorFlow is that you don't have to go through this calculation anymore. So you never have to code this up, for one. You don't even have to know what the chain rule is. You can essentially optimize a model and have it sort of automatically compute these derivatives without you knowing how to compute a derivative. That said, I highly recommend you go through this calculation once. It's pretty useful for building intuition, and you would like to avoid treating something as a black box if possible, and it's really not that complicated. So I recommend going through it. Let's see. Question: going back to optimizing gradient descent, don't you have to go up if you're stuck in a metastable optimum? What about increasing the learning rate to escape the local minimum and so on? These are really important questions, and the idea of having the stochastic part of SGD be there to add noise to help you tunnel out of metastable minima is an important idea that's been around for a long time. What I'll show you in a couple of slides is that this issue of metastability is actually not a problem for modern neural networks, and that's one of the surprises. Oh, let me see. So let me go through the next two slides, and we'll take a quick break. So I've given you here basically a 3-slide, introduction to a giant, fast-moving field of machine learning. I've omitted almost all of it, just to give you the bare bones that is going to be useful for us later on. In particular, I want to emphasize that I've omitted things like adding architectural structure, such as adding what are called convolutions that build in nice properties like translational symmetry and locality directly into the architecture. And this idea has been around for a long time and is really central to the success of neural networks on images and many other types of data that have these properties. Then in more recent years, there have been a number of developments that have helped train neural networks and help them generalize better, including things like something called batch normalization, adding what are called skip connections, carefully initializing the parameters so that you don't end up with trouble, either potentially metastable minimum or just unable to optimize because gradients are not computable, as well as a schedule for the learning rate. So there's this question about increasing the learning rate, and so having a schedule that sets the learning rate not just at the right constant value but actually dynamically is also important. And many of these developments help avoid something called the vanishing and exploding gradient problem. So if you go back to this mass of equations for backpropagation, I'm not going to go into these in detail, but there are these quantities delta, and delta at a previous L inherits from the later L. L stands for layers here, and they're multiplied by a derivative of some unit activations. And so you see you're going to get the products of many derivatives. And if you have a really deep network with dozens and dozens of layers, you're going to have dozens and dozens of products of derivatives. And you'd have to get pretty lucky to have that product not be very large or very small. In practice, computing these derivatives to get the gradient is problematic. And these developments in the last five years or so have helped get around this problem. The last thing I want to say before we take a quick break is, neural networks have been around for a long time. So what's different? The thing that you often hear, and I will just say the same thing, is that for one, we have a heck of a lot more computational power. In particular, the use of GPUs, which are well suited towards the kinds of computations that need to be performed. And this is really important because together with having a lot more data, neural networks really benefit from having more compute and more data, more so than the approaches like support vector machines that were popular in the previous generation. So when you have very small amounts of data, and a small computer, maybe a neural network isn't the best thing to do. But once you're in this regime of big compute and really big data, neural networks seem to dominate. Additionally, let's see. I'm hearing that the audio is having trouble. Can someone else hear me?
We can hear you.
Okay, great. Additionally, one doesn't want to diminish the contributions in the past decade or so that have really moved the field forward. So it's really not just the same as 30 years ago. There are a lot of new developments. Okay, so where I'll leave you for the 10-minute break is to say, it's great. We have these neural networks. They seem to work really well. They're extremely popular. But what's exciting from a theoretical perspective and for a physicist perhaps is that they often defy our understanding, and they go against a lot of the things that I told you about in the first part of the lecture today, leaving an opportunity for theorists to understand what's going on. So in the last part, when we reconvene, I'll tell you about some of those new things, new observations that seem to defy what we thought 10 years ago. Okay, great. So let's take a quick break and start up again at 12:20, and I will be here to answer any questions that you might have. These models do work quite impressively in many scenarios, and there are a number of sort of puzzles in how they behave that I think leave an opportunity for theorists to try and understand in the coming years. So I just want to give you a couple of those, and then we'll stop for discussion. So one example is there was a question a bit ago about getting stuck in metastable optima and having to add noise, increase your learning rate to tunnel out, and how do you know when to do that? How do you know when you're metastable versus just in the global optimum? And what what seems to be the case is that as you make these models bigger and bigger and bigger, so you go into what's called an over-parameterized regime, the loss landscape seems to get simpler. Oh, sorry, I realize I chatted not to that's the link I meant to send. So as you make the models larger and larger, their loss landscape, again, now I'm using loss synonymously with cost, gets simpler in the sense that the different minima that you might find actually seem to be connected in this giant high dimensional valley. So you might think that's not the case. You know, if you start, you initialize your parameters of your neural network, you do SGD, and you land at some setting of parameters theta 1 over here, and then you reinitialize from another setting of initialization of the parameters, and then you do SGD and you land over here. If you just do a linear interpolation in parameter space, you will generically cross a region where performance is terrible. There's a big barrier that you would need to cross. But it turns out that you can find in these overparameterized models, you can find paths that connect the parameters that are learned that never cross any barriers. And this is kind of interesting, and it allows optimization to become simpler in these larger models. Another sort of even more surprising for me result is illustrated here. I'll try to explain what's going on here. The idea is you start, what you're going to do is you're going to start with two neural networks. You're going to initialize them the same at the same initial point, and then you're going to do SGD, and you're going to use the same data ordering, so the same choice of the mini batches, if you want, for a certain number of steps. So the models are really just identical. They're the same models. And then after that number of steps, you re-randomize, and they get different batches. So they get different noise. So they start with tied noise, and then they get different noise. And the numbers down here tell you how many steps they get tied noise before they get different noise. And then you train them all the way up till they're done. They land in some place, and then you do this linear interpolation, just like is plotted over here, between the models that you find. And what Jonathan Frankel and collaborators find is that if you untie the noise right at the beginning, so that you just give them different mini batches from the beginning, you get this picture like here, where as you linearly interpolate, you get this regime of really bad performance in the middle. But if you just go for, you know, roughly 2,000 iterations of gradient descent, where they're tied together, and then you untie them, you leave them alone, and they wander off in their own way because of the noise, they actually find quite different solutions. But the test error when you interpolate linearly between them stays essentially at its optimum. So not only are these models connected in a valley like this, they're connected in sort of a linear valley where you know, you can just linearly interpolate. You don't have to do anything fancy to find a path between them. So that's pretty interesting. These are empirical facts. This is data. Basically everything that I'm going to show you in the next couple of slides is empirical data that I find interesting, that goes against what I might have thought when I was you know, before I had seen this data. And I like to think of it like in physics, where someone says, "Hey, look, I found that if you set up an experiment this way, you can get charges that are, you know, not whole units of of an electron charge, and how does that happen? You know, these are empirical facts that demand some explanation. So another observation that people have found is that what I told you in the first part of the lecture about bias and variance and this U-shaped test performance, in this case it's called risk. I told you that's always called something different. You get the best test performance at intermediate complexity. That's the nice story. Don't use a model that's too complex or else you'll overfit. That story, in some sense, is out the window for modern neural networks. And there's now something that Belkin and company have called double descent, where as you increase the complexity of the model, you first have this classical regime that I described, but then you enter a new regime about when the model complexity is such that you can now fit the training data perfectly. And what happens in that regime is, you know, you would think that you're crazy to go beyond this. Like, you know, we already saw that the model is getting too complex. You're going to overfit. You're overfitting. You know, stop. Don't go any further. But if you're brave and you go even further, then the test error starts to go down again. And in some cases, it can be lower, way out here, than at this sort of local minimum here. And this sort of, you know, goes against a lot of the things that I told you in the first part of the lecture. And there are certain models that Belkin and others have studied that can explain where this comes from. I think a full sort of complete understanding of this phenomenon is not totally there yet. One thing that you can say for sure is that if you have a family of functions or models that is sort of nested, so that the models out here contain the models here. For, you know, if you're talking about polynomials, for example, and this is your 10th order polynomial and this is your cubic, you could certainly reproduce this model here with this model family out here. But the fact that you don't do that in practice, and that you get good performance for the bigger model, tells you that this behavior must have to do with optimization in some way. Why are you picking a model that is good when included in the set of things that you could have picked is a model that is much worse? So there's another recent paper by OpenAI where they complexity for you should think of as being related to the size of your model. Think of it like the order of the polynomial that you're fitting. So these are you know, low order polynomials. These are intermediate order polynomials. These are giant polynomials. Or if they're neural networks, they're neural networks with increasing numbers of units in each layer, and or increasing number of layers. So let me, for the other question, let me refer you to one of Belkin's papers where you actually can find this kind of behavior in certain instances with linear regression. So I don't have the exact details on top of my head, but like there's a paper by Belkin called something like 2 models of double descent, where he actually derives that for relatively simple settings. So this paper by OpenAI, they have formidable resources, and they showed that this similar kind of behavior of this double descent, where the test error in the solid line goes down, goes up, and then goes down again, and is in this case minimized at these largest widths, is a fairly generic phenomenon in modern deep learning, including in these supervised models, including in recurrent neural networks, I believe, including in transformer models, if I recall. This is a behavior that is not necessarily super fine-tuned. There are some things that you need to make it happen, but it is somewhat generic. They also find an interesting result, which is that if in this case they're working with something called a transformer, if you increase the complexity of the model, you actually end up with an intermediate regime where adding more data makes things worse. So this is meant to be counterintuitive, that you would think you should always do better, but in fact you can find a regime where adding more data makes things worse. The idea being that this dangerous regime here is near this interpolation threshold, and that where that is going to be dependent on how much data that you have. And as you get more data, you actually you move the interpolation threshold. So for a fixed model family of intermediate dimension, here you might be sitting to the right of this this peak here, but then as you add more data, you move the peak to the right, and you actually now made the model perform worse because it's now in that critical bad region. So another surprising result comes from a paper by Zhang et al. From a couple of years back, where they took data like this is CFAR 10, which is a bunch of little images that are broken up into 10 classes. These are the 10 classes, and you can take a neural network, train it on this data, and give it the true labels. So all the airplanes are labeled with a one-hot representation of 1, 0, 0, etc. The automobiles are 0, 1, 0, etc. And it will fit the training data well. And then when you ask it to make predictions on the held out data, on the test data, it will generalize well. It will perform well. But what you can do is you can take the same training data and you can randomize the labels. So this airplane is called a cat, this airplane is called a horse, this airplane is called a dog, and so on. So all of the images get a completely random label. And you can ask the model to fit those random labelings. And the surprise is that in this plot here, that is the red here for random labels. The loss as you train, it struggles a bit. There's a lag, but after that lag, the loss goes down and the performance is essentially perfect on the training data. So it's able to memorize these random labelings. And in this case, there's nothing for the model to learn, in the sense that there's nothing for it to generalize to. If you give it test samples that have the true labels or random labels or whatever, like, it's going to give you chance performance. It didn't learn anything that is useful for generalizing. It just memorized the labels. So what's surprising is that you have a model that is flexible enough that it's able to successfully memorize random labelings. But when you give it true labelings, it soaks those up, it memorizes those, but it doesn't just memorize them, it actually learns something that can generalize to the test labels. And so this goes against, what you would think from classical learning theory, and that's why they titled their paper that understanding deep learning requires rethinking generalization. And this paper now is a couple of years old and has really galvanized a lot of the community to work on these questions.
David?
Yeah.
Sorry, before you move on, I think there are some questions on the chat
Oh, I'm not seeing anything new.
Um,
From Kaita, is that the last one?
yes. Or maybe, did you answer? Sorry, maybe I missed that.
Oh, sorry. Yeah. Yeah. I think I in my in my
Okay.
description answered
Okay.
these questions.
Okay.
Cool. Um, so the last thing I want to mention is a kind of interesting experiment done by Tom Goldstein and company at University of Maryland. And what they did is they said, if we train these neural networks via SGD, they seem to find solutions that generalize well. But do there exist models that fit the training data but generalize poorly? So this is sort of a corollary in some sense from the last slide. So what they did is they took training data with the true labels, and then they poisoned the data set by adding to it the test set data with randomized labels, so that if they were able to find a model that could fit both of those, then they'd have a model that trained perfectly but tested terribly. And they found that they were able to accomplish that. That these models were flexible enough that they could fit the training data perfectly and fit test labels terribly. And so what this paper sort of emphasizing is that this is sort of like a visualization of the models during training. The sort of reddish colored models are the ones that were actually the models during training, and the blue ones were the models where they try to poison the models by finding bad generalizing optima. And what you're supposed to take away from this is that there are settings of the parameters that fit the training data great but generalize terribly all over the place. They're sprinkled all over, and the optimization that we're using avoids them and brings us to a region that generalizes well and manages to not get stuck, not end up with one of these poorly generalizing models. So I think that's everything that I wanted to tell you today. So just to recap, I gave you a sort of whirlwind introduction to what learning is versus just fitting points. I gave you a quick introduction to the Biasvariance decomposition, which we later, said doesn't necessarily hold for modern neural networks. We talked briefly about what neural networks are and how you optimize them, and we went through some of these modern mysteries. Let me again emphasize that I didn't, in most of the talk, I didn't have much in the way of references, because this material is directly from this long review, and you can find abundant references in this review. And I really encourage you to go to this site where you can find the Jupyter notebooks that go along with much of the material in that review, including the little sort of examples that we had in the very beginning. So yeah, thanks very much for sticking around, and I'm happy to answer any questions about this material, about other things related to machine learning and physics, anything anyone is interested in. So I think to a first approximation, saying anything about generalization, I think to a first approximation we don't know that we don't know much about generalization. So I don't know if I can say anything insightful about how architecture should affect generalization in this this regime where you have a very large number of parameters. You know, these are really interesting questions, and you know, get right to the you know, right to sort of cutting edge research. So the difference between doing a let me go back. The difference between doing this random labeling and this sort of data poisoning, model poisoning, if you want, is that here this experiment was doing randomizing the labels on the training data, and this is just going one step further and saying, let me keep the labels on the training data. So I want to actually perform well and like predict the training labels correctly, but I want to see whether my model is so flexible enough that I can find settings of the parameters that will do that, and then also generalize poorly. And so one way to find that is to just explicitly take the test set, which is how you're going to measure the generalization, and give incorrect labels. So it's, as you say, it's very similar in flavor. You might not be surprised that that this happens, given that you can fit random labelings on the training data. But it's a nice illustration that that optimization is really important, in the sense that if I consider the set of neural networks that that fit the training data perfectly, that set contains models that will generalize well and models that will generalize poorly. Sort of an existence proof that there are plenty of models around parameter settings that are in that set that fit the training data that generalize terribly. And so this sort of says that, again, optimization, selecting for you amongst that set, the ones that generalize well, is really fundamental to why neural networks work. Let's see. So I think so. In general, you know, there's always a tension between doing theoretical work that you think provides insight into how something is working, and developing models that or frameworks that perform better. And you know, it's true. You know, the question is from Megan, is asking, I think, you know, if you can do well without understanding things, and if understanding doesn't necessarily give you better performing models, like, you know, it's, you know, it can be maybe difficult to get people to pay attention. And, you know, that's definitely, you know, something that you have to contend with. The hope is that by understanding something, you ultimately do end up making it better. And maybe you don't improve the performance of something in the same paper in which you're doing some theoretical work, but you know, the hope is that having theory and having you know, new understanding of how these things work can help to improve their performance and develop new methods in the future. these are long questions. Let's see. So this question is asking about adding noise, not to the outputs of the model, but rather to the parameters. As far as I know, and this sort of connects to similar in flavor to a previous question on having multiplicative noise or something like this. I think these are good questions. I'd have to think about doing a similar derivation in that sense. It's most straightforward when you just add the noise to the outputs, but there's probably something similar that one can do when you add noise to the parameters. So the question from Adam is asking a couple of things. One is about connections between some of these ideas and real brains, problems in neuroscience. I can say a couple of things. So one, people say that the architecture of neural networks and the structure of the units and so on is, very, very weakly informed by the, say, ventral visual stream. And, I think that's true. Whether that's an important motivation or not is, I don't know how to answer that. But you might say that although there are only a few bits of information that went from how the brain is structured to the neural networks, the neural network architectures that we have, there might be some very important few bits. There are many different kinds of models that you could study, and these seem to work quite well. So those bits might have been pretty important. There have been other sort of more recent than 30 plus years ago inspirations from neuroscience into machine learning. In particular, things like dropout, which is a regularization technique where you sort of randomly drop units in the network while you're training it. It's less used now than it was a couple of years ago, but it's still around. This was directly inspired by the fact that neurons fire spikes. They don't emit continuous signals. On the question of overparameterization in the brain, you might say that on the one hand, you might say, well, what I showed you was that overparameterized models optimize pretty well, and so what you should do if you're designing a brain is have it be overparameterized, which it seems to be if you count, do raw counts of number of synapses versus the number of seconds that you live or whatever. Make your model overparameterized and then regularize it well, either via the optimization or spiking or whatever. I think one should be careful because it's not. The brain almost certainly doesn't optimize via gradient descent. It largely works unsupervised as for a lot of its time, as you're pointing out. And it's questionable whether there's even an objective function. So a a lot of the lessons that we're learning from supervised learning in overparameterized models using gradient descent, it's one should be careful trying to generalize them to neuroscience, but it's very interesting. I don't know enough about GANs to tell you about the big open theoretical questions there right now. Ben's question about other techniques to compare to neural networks, the sort of standard contrast between neural networks is using things like kernel methods or support vector machines. And I think the story there that you often hear is that as I was saying before, these methods work quite well when the amount of data that you have and the amount of compute that you have is smaller, and neural networks seem to be good because they are able to take advantage of all of the extra compute and all of the extra data. That said, another reason why support vector machine approaches were very popular for a long time is that there is a very nice theory that is fairly well worked out by many people for them. So in a sense, you might say they're better understood. So there were sort of two, similar questions about either coarse graining or the renormalization group. So I have a paper from 5 years plus ago now, making a connection between a certain kind of renormalization group approach and a certain kind of deep learning approach. That paper sort of came out approximately when the deep learning approach that we were connecting to had sort of lost excitement. This was in an era where these issues, like go back, of being over-parameterized and having optimization be relatively easy, were not recognized, and there was a lot of concern about finding good initializations. So we still need to find very good initializations, but we don't need to do that with data anymore. In the old version from like 10 years ago, people did sort of stages of unsupervised learning to find parameter settings that have absorbed a lot of information about the input data that could serve as good initializations. And what we had found was that there was a connection between this unsupervised learning stage and RG. After that, in the intervening time, there most of the work that was really successful in neural networks for a number of years, the low-hanging fruit at least was in supervised learning. That's not exclusively true. There are GANs and all sorts of other things, but a lot of it was supervised. So there wasn't that much attention to those kinds of things. Now, in the past year or two, unsupervised learning in neural networks has been coming back. The most popular thing is now called self-supervised learning, which is very exciting and interesting. And a postdoc Wave in my group has been doing some work that we think connects something that looks like an information theoretic version of RG to self-supervised learning. In terms of purely supervised learning, there is some work on very wide neural networks. And in the limit where the width gets very large, things simplify and you get nice properties. And then when you peel away from that, and then you go to finite but wide, then you end up with something that might have a flavor of RG. There's a paper by Shoyaida that's very nice, called non-Gaussian processes and neural networks at finite widths that makes a connection to renormalization group. So let's see. There are a couple of questions about. There's one about how things like chaos theory or random matrix theory informed deep learning research. For that, since I'm running short on time, maybe I could refer you to Tankut Khan and Kamesh Krishnamurthy, who are postdocs at the ITS and at Princeton, respectively, who have been doing work on those things recently. That's super interesting. So you should write them. If you can't find their emails, let me know, and I'll send you to them. There's a question of is information bottleneck related to RG? This is something that I have been working on recently. Roughly speaking, in RG, you try to find if you want a compressed or coarse-grained representation of a system that retains predictability of long wavelength physics. In information bottleneck, this is a version of rate distortion theory where you try to compress some input data while preserving information about something else that you care about. So you can imagine a connection where the thing that you care about is long wavelength physics. But again, trying to make that connection precise is something that Wave is working on. Probably the last question, and then we'll wrap up. You can increase network complexity via width or depth. What are the differences in the context here? They, in some senses, are quite different. When you go to large width, you reach things get simpler. You should look up things like Gaussian processes, which is in a Bayesian framework, something that happens when you go to infinite width. If you're doing gradient-based training, you get something called the NTK. When you have very deep models, you can enter into different regimes, and certainly when you go very deep, you have these additional issues of optimization, right? So the vanishing exploding gradients are going to be much more problematic. So going to very, very deep networks, you have to worry about those things more than going to very wide networks. Great. So I think we're at the stopping point. So maybe if you have other questions, we can save them for. We'll have another section of a chunk of time at the end of tomorrow's lecture to discuss more broad questions. Great. So thank you all, and I will see you tomorrow at 11.
Thanks, David.